I think we've had at least 70 bookings, so lots of people are coming, which is great. And also it's testimony to Karen's work, which speaks to so many people on our campus, but much beyond. So it's going to be a really great state of the art today. Karen actually started at the university in 2004. She was one of 5 geographers I've just discovered who set up the geography department in 2004. And this means it's a great privilege for me to introduce her today because we are colleagues in geography as well. And she was one of the most welcoming staff when I was looking at coming down here. So I'm very grateful to Karen for welcoming me in. And she's been here for 16 years doing amazing work and is very central to the ESI because she's pioneered the use of remote sensing equipment and data for understanding ecosystem change at the landscape scale. She's going to give you a brilliant overview of everything she's been doing today. And then we'll have about 10-15 minutes at the end for Q&A and questions. If you want to get in early, put your comment or question in the chat and I can come to you first. Otherwise, it will be a hands up open floor for the last 10-15 minutes. So that's enough for introduction, I think, but it's a great pleasure to have Karen with us today. Her title is From Leaf to Landscape, State-of-the-Art Remote Sensing for Monitoring Ecosystem Dynamics. So over to Karen.
Thanks, Jane, for the introduction, and thank you so much for inviting me to do this. It feels a bit daunting, actually, and I can't quite believe I've been at Exeter for 16 years, but yeah, it's been a good time. And I want to say thanks to Amrita for doing all of the publicity around this. Amrita's done a fantastic job on social media and stuff advertising this talk. So thank you, Amrita. That's really nice to work with you. So yeah, so I'm going to talk today about leaf to landscape remote sensing, particularly with a focus on ecosystem dynamics. And as Jane said, I'm a geographer, but I'm also an associate professor in the ESI, and my work is really concerned with evaluating patterns in vegetation across time and space. And so in this session, I hope to kind of give you some broad examples of the kinds of systems that I work in, and also some inspirational examples of how we can use remote sensing to transform our understanding of vegetation systems. Because, you know, I'm kind of aware that this is quite a diverse audience, I'm not planning on going into a lot of detail on methodologies and the sort of specifics of how we process all of the data. I will provide links to the papers that sort of give those details. If you want to read them, of course, you can kind of ask questions at the end as well. So I hope my slides are turning. Has that slide changed? Hopefully.
Yes, it has.
Okay,
yeah.
Great. So I was kind of drawn to this field of work because I'm really interested in patterns of things. And if you look across these different examples of systems that I've worked in on the slide here, then you'll notice that they kind of show really interesting and complex patterns in the plants and soil. And those patterns will be related to all kinds of other things. So, for example, the way water moves through the landscape, or the amount of carbon that's stored by or exchanged by the ecosystem. And so I think patterns in vegetation are really, really interesting. You'll notice from looking at these pictures as well that my work is not really about big, charismatic, tree-covered systems. Instead, I like to champion systems which have small plants, and those systems sometimes are overlooked. But just because the plants are not that big, these systems are still really important. They can be highly sensitive to climatic change and to human impacts, and yet they're generally poorly represented in both remotely sensed products and also undersampled by in situ monitoring. And that's a bit of a gap because current global change threats emphasize the need for new ways of capturing information about these systems at appropriate spatial and temporal scales. And so that's what my work seeks to do. And so hopefully in this talk, I can shine a bit of a light on these little plants, and maybe by the end, you'll agree with me that they are really important. So in the next couple of slides, I'm going to give you a very quick overview of a couple of key concepts in remote sensing, because I'm aware that there may be people in the audience who haven't come across remote sensing before. And these will kind of underpin some of the science methods that are used in the rest of the talk. So what is remote sensing? Well, it covers lots of things. It's a very broad field, but we can boil it down to the measurement of Earth system characteristics over different scales in space and time, using sensors that are sensitive to electromagnetic radiation, or generally speaking to light. So these are sensors that record light, cameras and other radiometric instruments. And we can deploy those sensors on board a range of different vehicles or platforms like the ones that you see here. And those different platforms afford us variable opportunities in terms of data resolution in both time and space. So close to the ground, we might consider something like a drone, for example, where we get very fine spatial resolution from those sensors, and we have relative flexibility in how we can deploy them and how frequently we can deploy them. But the coverage is compromised in such examples. So with drones, we might only be able to cover a few hectares per survey compared to a satellite, which provides us with almost global coverage. Further away in space, when we look at satellites, we get very predictable revisit periods to the collection of data. So some satellites might be able to give us data every few days. Others are a bit less frequent. But the sensor is obviously further away from the Earth system, and that generally means that we get coarser spatial resolution, but better coverage, i.e. bigger areas are imaged in a single acquisition. And so when we're thinking about the types of applications that we might want to use these different types of data for, it's really important to select the right system for the job and to think about those spatial and temporal constraints. So what other kind of information can we get from remote sensing? Well, one of the things that really amazed me as an undergraduate when I first started learning about remote sensing was this. And of course, with remote sensing, as I've already explained, we're using systems that are sensitive to light. And in many of the Earth observing systems that are used on satellites, all the way down to drones, we're measuring reflected light. And when we look at reflected light, particularly over plants and vegetation, the amazing thing about remote sensing data is that what you're actually seeing is a direct view of photon interactions with plant biochemistry and also leaf structures. So when we look at the way that plants reflect light from the sun, the low reflectance that we see across the visible region in healthy plants relates to photon absorption for photosynthesis. And in the near infrared, which is beyond the scope of human vision, we see here in the grey part of the graph, the photons are very strongly scattered by air spaces within the spongy mesophyll, and that's because inside the leaf, the air spaces are basically a sort of similar size to the wavelength of the radiation in this part of the spectrum. And so in healthy vegetation, you notice that there is a big difference between visible and near infrared radiation, and this forms the basis for a whole range of products that we can derive from satellites all the way down to sensors on drones called vegetation indices, of which the most common one is the Normalized difference vegetation index, which ratios these two parts of the spectrum to each other. And you'll notice that in vegetation that's senescing or is less healthy, in the brown line on the slide there, there is a smaller differential between the visible and the near infrared reflectance. And so using that as a basis, we can generate very generalized products which tell us or provide a useful proxy for vegetation status and health. And so this underpins some, but certainly not all of the work that I'm going to be talking about in some subsequent slides. Now, in addition to the fact that we might want to know about the kind of biophysical status of vegetation, equally we might want to know about plant structures and how they change spatially or through time. And by this I mean height, shape, volume type characteristics of vegetation, because those relate to all kinds of different useful plant traits, for example, above ground biomass. And we can measure this using remote sensing with two different methods. Firstly, using laser scanning devices, or LiDARs as they're commonly known, which send out an active beam of light from the sensor itself. That light interacts with the vegetation, and usually we get a couple of measurements, one from the top of the canopy and one from the ground. And using that, we can measure certain characteristics of vegetation structure. Secondly, we can also do this using a relatively new workflow, which is called digital photogrammetry. And this is typically done from a drone carrying a normal imaging camera. It's a passive remote sensing method. So we're simply capturing aerial photographs which overlap with each other. And we can use those data to generate novel products that tell us about the structure and the height of vegetation canopies. It produces a similar, but it's not exactly the same type product to the laser scanning workflow described on the left of the slide. And what this does is it uses information contained in the image parallax. So that is the difference in the apparent position of objects in the scene according to the varying viewpoints at which those images are collected. And it uses a kind of computer vision workflow to generate those photogrammetric products. Okay, so just to summarize that's the end of my kind of introduction, really. Using remote sensing of vegetation, we can measure dynamics in space and time using different sensors or platforms. We can measure leaf and canopy physiology and biochemistry using spectral information, and we can also measure canopy structures using laser scanning or photogrammetry. So now what I'm going to do is kind of take you through these varying scales of observation to give you some examples of work that's been done within my research group. And I'm going to start at the really fine scale with drones and then work up eventually to space. So in this section, I want to highlight some of the work that we've been doing with drones, and we're going to start in the US deserts, looking at generating products to quantify biomass, and then we're going to move a little bit closer to home with some spectral products to look at plant phenology. Now, drones really provide us with very fine spatial resolution data, and this is a relatively new workflow in remote sensing. So 10 years ago, although drones did exist, they were not really widely used in science. And over the last 10 years or so, there's been a huge upsurge across biological and geoscience disciplines where the drone has really become, quite an essential tool in the workflow for gathering spatial data. And that's because these systems are relatively cheap to buy and relatively easy to deploy. And unlike the other types of remote sensing platforms, we can deploy these on demand. So, as scientists, we are in control of the data that we're capturing with these systems. They do have some limitations, particularly in terms of the extent coverage. So really, with most drones like this DJI Phantom 4 that we see in the picture, the coverage per flight is maybe a few hectares, and if we want to build up a picture of a very large area, it would be quite inefficient to do so with the drone. Nevertheless, the cost of the technology and hardware is relatively cheap, so between about £500 up to about £10,000, depending on the sophistication of the sensors that are used. So just before I kind of show you some of the examples of what we can do with these systems, I just wanted to kind of put a bit of a health warning up to say that actually often the drone is kind of couched as a low cost technology. And that's absolutely true when you consider the actual cost for buying the hardware of the system, the drone itself. But that's only part of the story. If you really want to invest in drone technology as a means of producing really high quality spatial estimates of vegetation or indeed anything else, then there's a whole kind of workflow that sits behind the acquisition of those data and underpins that kind of high quality data production. And so it's not just simply a person and a drone that delivers those high quality end products. We really need to calibrate our sensors, we have to geo-rectify our products, and we have to generate validation data to make sense of those products. And so when you buy into drone technology for generating these spatial data, then you really are buying into the entire workflow from the design and acquisition of the data through to the generation of the products. And that can quite easily be overlooked when you're thinking about the cost of doing so, because actually some of these components that you see on the slide here are considerably more expensive than the drone itself. And so that's an important consideration. Okay, so let's start with a relatively simple example of where the drone can deliver really unique insights into vegetation patterns and help us to kind of understand vegetation systems. This is work that was done by a PhD student of mine a few years ago, James Duffy, and it uses a very basic consumer grade drone called a 3DR Solo, and that was fitted with again a basic kind of point and shoot camera, the Ricoh GR. And of course, one of the big advantages of drones is that they're small and agile, and we can use them to survey areas that would be otherwise difficult to reach. So in this case, James undertook a project to map seagrass beds over some intertidal mudflats. In this case, these were in South Wales, but you could quite easily translate this methodology to intertidal species mapping anywhere in the world. And the reason that the drone is so great for monitoring vegetation in these settings is quite simply that these are quite perilous landscapes to do field work in. In this particular case, these mudflats were only exposed for a couple of hours at low tide. And so actually getting estimates of the total seagrass coverage in these systems was impossible by any other means. We can't do this with satellite remote sensing technology because they tend to be very small habitats, and as you can see, there's lots of heterogeneity here with mixed pixels that we might get with a satellite, for example, mixtures of mud and vegetation. And so with the drone, we were able to produce really high accuracy maps of seagrass coverage over these intertidal mudflats. And if you want to read more about that, the paper that James produced is shown at the bottom. So that's a basic sort of photographic workflow. All we're simply doing there is stitching the photographs together and then using a classification algorithm to automatically discriminate plant matter from non-plant matter, and then using that to kind of scale up to an estimate of seagrass coverage across the mudflat. But using exactly the same system, hopefully you can see the animation playing on your screen. We can also execute slightly more sophisticated workflows with the same sorts of data. So using aerial photography, particularly aerial photography which shows, or rather which has a very high kind of overlap and convergence in those imagery, we can generate photogrammetric products which tell us about the volumetric nature of the vegetation in systems like this. Now, this is a dryland system. It's located in the Exeter National Wildlife Refuge in New Mexico, and Andy Cunliffe was doing his PhD there, and we've since had a NERC project to extend that work. What you can see here is a rendered point cloud which shows creosote bushes and grasses within this dryland system, and we generated it using those photogrammetric workflows applied to these overlapping photographs captured from the drone. In this project, what we were doing was trying to improve understanding of the dynamics of vegetation in dryland systems. And remote sensing is one small part of a much bigger project, which involves carbon measurements and modelling in these systems. So let me move to the next slide. So the great thing about this technique is that using photogrammetry, we can derive volumetric estimates for individual plants. And we can then apply that across relatively large areas to understand something about the volumetric ecology of these ecosystems. That's important because one of the questions we're trying to ask in this project is, how are these systems changing in response to climatic change or other drivers? And of course, the above ground biomass is very dynamic in dryland system. It responds very quickly to changes in rainfall and changes in temperature. And so we can use that to understand something about the carbon system dynamics within these complex ecosystems. So what we see here is the ability for this photogrammetric workflow to reconstruct volumetric estimates of the size and shape of the plants. Okay, we can measure their height, we can measure their volume, and we can do that relatively accurately if we deploy in this field a range of markers that tell us about the exact positions of things in the field. And what we can then do is we can use measurements that we've gathered by destructively harvesting some of these plants within the experimental plots. We cut them, we dry them, we weigh them to determine their above ground biomass, and we can relate these metrics that we derive from the photogrammetrically derived products to critical variables like above ground biomass, and that's what you see on the graphs on this slide. So it makes it much easier for us to develop methods then that allow us to non-destructively revisit these sites and chart changes in the biomass dynamics of these systems over time. And that's quite a sort of revolutionary approach, because up until we kind of demonstrated this technique in these US drylands, people were having to go out and destructively harvest plants and weigh them every time, and that doesn't give you spatially distributed estimates of your carbon stocks here. So we've also, in doing that, developed individual allometries for particular species that haven't so far been done. So the example at the bottom of the paper there is we perform this for juniper, a juniper species using photogrammetry as part of the workflow. So that's really how we can use these fine-grained products to tell us about plant structures and, carbon dynamics. I now want to move on to show you an example of how we can use slightly more sophisticated sensors that are a little bit different from just basic digital cameras to understand time series dynamics in variables like plant phenology. So here we have some work that was done by a PhD student of mine called Dominic. We used this radiometrically capable sensor called the Parrot Sequoia, and we flew this over a mixed woodland located in Cornwall. We did that multiple times throughout a year. And what we were seeking to do with this project was to determine whether we could determine individual species phenologies using the fine-grained data from the drone, coupled with this regular revisit period that we could fly every few days throughout the growing season, for example. So what you can see on the left-hand side of the slide is a sort of depiction of the variability of the scene. It's a false colour infrared image, so it looks quite strange. It's captured from the peak season, and bright pink pixels are the trees that have the most leaves. Basically, they're the most sort of photosynthetically active trees. And next to it is a map showing the distribution of the different species across that site. Now, what you see on the bottom right of the slide are a series of plots that chart the day of the year along the x-axis, and then that changing NDVI, that index which tells us about the vegetation vigor, the difference between the near infrared and the visible region of the spectrum. And what we see is that from these time series data captured from the Sequoia, we can depict quite clear differences in these time series graphs between different species. In particular, you notice there's a big dip in hawthorn around mid-May, which is the dip that you see just here. Let me just bring my mouse to life for a second. Here we go. No, it's not going to let me do it. Whoops, sorry. Hang on. So yeah, this dip just here, this is caused by the onset of flowering in hawthorn, which gives rise to a reduction in the value of that vegetation index. We also see some species which show quite a lot of variability, particularly at the beginning of the season, and that's because we're looking through the canopy actually to the bottom of the woodland, and we're seeing some of the green up in the understory. So we're picking up all kinds of different patterns and processes with these data, but we can generate relatively simple models to apply and fit kind of sigmoid models to those data to estimate things like key phenological parameters like the start of spring or the start of peak greenness, and we can do that on a per species basis and also look at spatial variability across the site. So this was the first time that really those kind of spectral indices had been applied over really fine scales to individual tree crowns, and it's really the drone scale that gives us a unique opportunity to do that kind of work. It would not be possible to do this with airborne data because it would be far too expensive to capture multiple acquisitions from a piloted aircraft through the season, and from satellite data, the resolution is far too coarse in grain. So again, if you want to have a look at the details of that, the link to the paper is provided at the bottom of the slide. So now I want to move on to the airborne scale, which provides us with landscape indicators of vegetation state. And when we talk about airborne data, we're talking about data with a spatial resolution of about 50 centimetres to around about 5 metres. It may be coarser than that in some cases. But there's a much greater array of different sensors that we can deploy on aircraft because they're obviously larger, they can carry heavier payloads and so on. We're very lucky in this country, quite a lot of data available freely to us as science users, and we can access those through the government website, data.gov.uk, or through other kind of open source suppliers. If you want to commission your own new survey of these data, they can be very expensive, up to £10,000 for a single acquisition. So given that, you can see why the drone has kind of risen in popularity as a platform of choice for scientists, because for bespoke applications, airborne data can become very expensive. That said, given kind of freely available data, I'm going to show you some examples of the sorts of work that we can do. And there's quite a heavy focus here on systems in the southwest, because we've been working a lot with a group based at Exeter, including Richard Brazier and various postgrads and postdocs who've been advancing this work considerably over the last few years. So I first became interested in using laser scanning to measure peatland hydrological status about 15 years ago. And way back then, just after I started work at Exeter, I had a new investigator project funded by NERC, which kicked off this whole bunch of work on researching peatland surface structures as proxies for hydrological functioning. And back then, no one had really tried to use LiDAR to measure the condition of peatlands, but it's kind of quite obvious really when you look at it, because when peatlands become degraded, one of the first things to change is the surface morphology. And it can be quite a good indicator of the underlying hydrological status. So when the water table in a peatland drops, we see a change in the surface structure, and a change specifically in the length scale of the surface structure. You can see that kind of depicted in this diagram here. And when that surface structure changes, we see degassing of carbon, methane from peatlands. We see loss of carbon in runoff through these gullies and erosion features. And so actually being able to map the distribution of these using remote sensing is quite powerful. Now on the left-hand side, what you can see is a kind of enhanced surface model derived from LiDAR laser scanning data of a section of peatland on Dartmoor. And you can probably see the structures that are visible with your own eyes. So let's bring those to life. Oops, hopefully you can see that. Now, all of these different coloured areas that you see on the slide relate to the changes in the structure of the surface and the hydrological status. They are things like peat cuttings, erosion gullies, and drainage ditches, for example. And so I want to move on to just show you how we've kind of expanded that study. Donna and Dave Luscombe have been working on this, and this is very much a manual task. So we haven't simply put a computer to work to find these features. It's very challenging to do that automatically. It's much more of a kind of manual mapping task. But we have taken on the task of mapping all such degraded features across the Dartmoor peatland area. And this was part of a South West Water funded upstream thinking project, and also linked to the national park. And we combined data sets, including LiDAR, but also including other remote sensing data, all acquired during the TELUS Southwest survey project. And the headline finding from that work was that in total, an area which covered 29 kilometres squared, or 9.2% of the Dartmoor peatland area, was identified as being significantly and directly eco-hydrologically degraded. And that's important because these degraded peatlands are a massive source of carbon to the atmosphere and into water sources, and 80% of the UK's peatlands are now classed as degraded, which is something we need to change and address through management, restoration and re-wetting. And so that was the kind of driver behind generating these products, was to kind of feed that into a broader restoration project that's ongoing on across Dartmoor and also other moors in southwest England. I want to just show you how we can sort of also add information to that though. So this is another piece of work that was done by Dave Luscombe as part of his PhD. Here, what we did was actually added in some extra thermal data. So in the very long wave part of the spectrum, we can detect thermal emissivity from surfaces. It's much like the kind of thing that you would do with a thermal camera, but slightly more sophisticated because this is a thermal radiometer. Now what you see across this image just here are patterns of red and blue. Blue areas are drier, red areas are wetter. And this product is the kind of end point of a whole series of processing steps that Dave followed. And of course, we did quite a lot of validation at this particular catchment site. And it tells us about the amount of water that's present in the near surface part of the peatland. Now, consequently, we've done quite a bit of mapping, and we know that this drier area, which is shown in blue at the top of the catchment, actually has quite a lot of drainage features in it. And this area down here, where we see these more kind of naturalized looking channels of flow, is an area that's relatively undisturbed. So we can immediately see the kind of impact of human activities on this catchment and on the distribution of water in the near surface soils. So this is another neat experiment in peatland work, also on Dartmoor, and this is where Naomi Gattis combined LiDAR-derived metrics which were known to influence peat accumulation with an additional product which was called gamma-ray spectroscopy. And gamma-ray spectroscopy data was collected over the whole of southwest England, again as part of the TELUS survey in 2013. And that was a survey that was primarily sort of targeted at looking at geological, the distribution of geological features across southwest England. But Naomi in her reading also discovered that we could use those gamma ray spectroscopy data to correlate with peat occurrence, and particularly to also develop a novel method for determining peat depth across Dartmoor. And so the headline of this particular piece of work is that over the entire Dartmoor extent, she applied this method and basically worked out that over an area covering about 406 square kilometres, which is the whole of Dartmoor, about 158 kilometres squared comprised peaty soil of more than 40 centimetres deep. And the critical finding of this is that most of that area of peatland that she discovered, so about 60 kilometres squared of that 158 kilometres squared, was overlain by grassland. And therefore, if we were simply using basic land cover mapping techniques, it may have been missed as being kind of peat forming vegetation. And then subsequently, what Naomi did, which was really cool, is that she used published bulk density and carbon content values to estimate the amount of carbon stored in these peats, which totaled 13.1 megatons. So, so we can not only map peat structures, we can also map patterns of peatland degradation, but we can also determine critical parameters like peat depth and carbon content over relatively large areas. So that was peatland, and I now just want to spend a couple of minutes showing you how we're translating some of that laser scanning work and expertise that we've developed on Dartmoor into other heterogeneous systems. So first of all, this is a project which is seeking to kind of address questions about trees outside of woodlands, and this is work that's being led also by Dave Luscombe and Naomi Gattis for the SWEEP project. And we're rolling this out over the North Devon Biosphere Reserve and the Dartmoor National Park to map the distribution of trees from LiDAR data and labelling them simply according to various criteria like height, fragmentation, and so on. Now, this is really great because it provides us with a baseline map of vegetation distribution, but it would be very expensive for us to commission resurveys of these sites every year to look for change. And so what we're now doing is adding in freely available satellite data to that analysis. We're constraining that analysis to the kind of areas where we have the LiDAR data showing us that we have certain trees, and we're looking for signals of change. So using Sentinel-1 radar data, we can do things like detect where trees are being felled for commercial woodland management. And we can also, we can also detect where things like hedgerows are being removed. And we have built a tool online that allows these various stakeholders to simply run those analyses on a fairly basic computer year after year after year for tracking change and identifying areas of tree loss, but also, of course, tree growth. So the final thing I want to say about airborne data kind of remains within these heterogeneous systems, but this I'm now going to take you to an urban system. And this was part of a project with Kevin Gaston, which was funded by NERC. And ultimately in this project, we were using LiDAR data to evaluate urban green space provision across 3 cities in the UK. Now, in contrast to the LiDAR system I just showed you, the LiDAR system here was a bit more sophisticated. And instead of just measuring the tops of the trees and the ground underneath, this is a waveform LiDAR system which measures everything in between those 2 points as well. So from the treetop to the ground, we get a time varying pulse, which with some careful maths and a bit of physics and lots of processing thrown in for good measure, we can determine something about the 3-dimensional distribution of vegetated components through the canopy from the treetops to the ground. And what this provides us with is something akin to a sort of Minecraft model of the world, which is why you can see that Minecraft picture at the bottom there. It provides us with voxels, which are these volumetric pixels stacked up in 3D. And ultimately what we can do with those data is we can kind of dive through the canopy and understand something about the density of vegetation distribution in 3 dimensions. Okay, so this was really quite amazing work that was done at the time by a postdoc of ours called Steve Hancock. And it segues me nicely to the final bit of my talk, which is about satellites, because after finishing that piece of work with us, Steve went on to work on the JEDI project, which is a really novel system that's just been deployed on the International Space Station. And the JEDI is a spaceborne waveform LiDAR. So a lot of the processing and signal processing techniques that Steve developed in our project on urban systems was then translated to this system on the space station, which is now providing global estimates of biomass and carbon across the world's forested ecosystems. And JEDI is a really cool system. I won't go into the details of it, but if you want to have a look at it, then please do. Google JEDI. It's a NASA sensor. So that leads me finally to the sort of last part of my talk, which is about satellite remote sensing. And satellite remote sensing is quite a different beast from the kind of data that I've shown you so far, because the spatial resolution is much coarser. And so typically when we talk about Earth observation sensors, we're talking about sensors with pixel sizes of about 30 meters up to about 1 kilometer in size. There are some satellite sensors that can provide us with data that are finer than that, but you generally have to pay for those data because they're from commercial suppliers. But the great thing about satellite data, of course, is that we have really predictable revisit times and for some systems, really great longevity. And the data are typically free if you're dealing with data from NASA or the European Space Agency. So one of the great opportunities that is afforded to kind of vegetation scientists like me is that NASA had the foresight to launch a series of satellites starting in 1972 with Landsat-1 that have provided us with a 50-year picture of vegetation change over a global scale. And these Landsat products, starting at Landsat-1 in 1972 and going up to Landsat-8, which is currently in operation around the Earth, give us a huge opportunity for monitoring vegetation dynamics at scale. But if we want to ask kind of questions about multi-decadal change in vegetation, we're talking about big data here. Okay, every single satellite image collected is, you know, megabytes, and so if you want to look at kind of changes in vegetation over decades, then you kind of need a very powerful computer to do that. How do we do that on a basic desktop machine? Well, that used to be a very difficult thing to do, but everything's changed in recent times because Google have done a really good thing. And they have launched this new platform for planetary scale remote sensing analysis called Google Earth Engine. And basically on their servers in Silicon Valley, they have amassed terabytes of satellite data collections from the major space agencies like European Space Agency and NASA. And if you want to access those collections and really have the kind of planetary scale analysis at your fingertips, all you need is a web browser and a Gmail account and a sort of fairly gung-ho attitude to typing code and seeing what happens in this window here. So it's reasonably easy now compared to 5 years ago to execute large-scale analyses to answer big global questions about change. And we've been doing that over 2 areas of the planet. And exploiting the capability within Earth Engine to do that. The first one is a site, or rather a very, very large site across the Himalayan mountains. And the second one is a project located in the Pan-Arctic, so covering high latitude regions across the Arctic from Canada across to Svalbard and the northern parts of Europe, basically. So in the Himalaya, what we're asking of these data, particularly these Landsat data, is has vegetation extent changed above the tree line over the last 30 years? And in the Arctic, we're asking the question, in these Arctic peatlands, has vegetation extent and greenness changed over the past 30 years? And so these are relatively simple questions. It's really just looking to see whether there are more pixels in these satellite data that are green now compared to 30 years ago. And the underlying reasons why we're working in those 2 places is firstly in the Himalaya, I'm interested in whether a change in the extent of vegetation at high altitude might link to changes in the sort of hydrological cycling of those systems. And in the Pan-Arctic, we have a NERC project which is looking at whether peatlands are expanding in these high latitude areas in response to climate change. So how do we do that? Well, there's lots of steps, and I'm not going to go into the detail of it, except for to say that we have to do quite a lot of data filtering. So we have to filter out data from certain missions, and in both of these studies, we're only focusing on data from Landsat 5 and 7. We filter them according to topography, we filter them according to date, and then we use a global NDVI product to determine whether a pixel is green or not. And we do that in different seasons because these are obviously different parts of the world. Now, what we found in the Himalayas was, firstly, we measured the extent of this system above the tree line, and we found that it covers 5 times the area of permanent snow and ice. So that indicates, first of all, that this is potentially an important area to be looking at in terms of eco-hydrology, particularly as the climate warms, and that exerts a very direct effect on the ecology of these high mountain regions. But secondly, we questioned how much has vegetation changed, and what we found was that since 1993, there has been an expansion of vegetation, particularly into the higher altitudes of these subnival habitats. So the strongest trend we found using these satellite data was between 5,000 and 5,500 meters above sea level. In the Arctic greening study, we have a selection of sites across the Pan-Arctic, as I've said, and at each of those locations, we're analysing a larger area which has more heterogeneous vegetation and a central area which is specifically known to be peatland covered. And at the peatland sites, we're also collecting drone data and peat cores so that we can establish local processes and rates of change. And what we found is that, and I should say this is ongoing work, that at different sites across the Arctic, there are different things happening. So there's kind of variable greening trends across these sites. Just a couple of examples here. Firstly, in Lapland, at a site called Karlboten, we see no clear greening trend, whereas in the Canadian Arctic, we see a definite positive trend in both the smaller peatland site in blue and the more heterogeneous site in orange. And so we're doing some ongoing work with this to establish what the drivers of change are. Okay, so just to kind of bring that to a close, really, I want to just show you how we're kind of also doing work that links these different scales of observation. So from the drone at fine scale to the satellite at coarse resolution. And what you can see here is work that Dominic has done for his PhD. This is a maize field in Italy, where we participated in a kind of campaign to link across these scales. And the first challenge you notice is that the sensors on these different systems are all measuring slightly different things. They're measuring different spectral resolution across the visible and near infrared range. But the good news from this project was that we found very good correspondences between products that were measured by the drone and products that were measured by the satellite. There is obviously some scatter because we're looking at products with different spatial resolutions, but these basic vegetation products tied in very well to each other. We found that was less the case when you started looking for more sophisticated indicators of vegetation, processes. So we were looking, for example, also at a chlorophyll index, which needs data around this region, the red edge, and those correlated much more poorly between these different scales, and that was largely because the sensors were measuring in slightly different regions of the spectrum. So to finish up, I just want to finish on a kind of interdisciplinary point, really, which is something slightly different from what I've talked about. And I was in two minds about whether to include that, but I think given that this is a state-of-the-art talk in the ESI, which is an interdisciplinary institute, it's important to kind of share this with you. And so most of what I'm going to say at the end here was born out of field work, particularly with drones, with me and colleagues kind of noticing a diverse set of reaction to flying drones for science. And we've been forced to leave sites and abandon data collection by raging members of the public, despite having all the right permissions in place. We've been asked to produce certificates of our flying competency, even though our research operations don't necessarily require it. And we've sat our CAA exams in various countries of the world. And I should say also that less than 5% of registered drone pilots in the UK are women. And so all of this kind of led me to go down a bit of a rabbit hole and into a bit of a critical deep dive into the drone and generally remote sensing research generally. And when you Google drone, these are the kinds of pictures you find popping up: drones delivering fried chicken, weaponized drones as vehicles of war, and so on. Drones as vehicles to spy on you and invade your privacy. But the science drone is missing in all of that. And I started to kind of question why, where are these narratives coming from, and what do we need to do as scientists who are using drones for completely different purposes? Well, of course, science drones are there, they're just buried. And part of my work has tried to take a bit of a lead in making visible some of the more positive uses of drones in conservation and science, and hopefully I've done a bit of that today. But the history of the drone gets quite interesting when you start to unpick it, because there's a whole evolutionary history to the kinds of technologies that I've just showed you, right? Not just the drone, but the remote sensing infrastructure that we're faced with when we come to do these geospatial analyses. And modern drones really kind of trace their evolutionary history back to the sort of aircraft that were doing reconnaissance missions during World War II. And of course, those uses continue today. But evolution is the key word. And this technology that we are now using for science has kind of morphed and shifted from those military roots. And now there's a whole bunch of drone phyla, if you want to think of it biologically, which comprise these different machines, which are all intended to do different things, from racing to fighting and to play and science. And that evolution is absolutely not unique to drones. Pretty much all of the technology that I've talked about today shares those military beginnings, like GIS and GPS and satellite technology, LiDARs, radars, aircraft, all of it. has a military ancestry, yet we've accepted the evolution of those tools in other areas of the geosciences, and now the drone is kind of having its day, and we've kind of lived through that as scientists who are practicing users of that technology. Now, this has another side to it too. Corporations are currently jockeying for access to the airspace above our heads, and this is happening right now. It's happening in Cornwall, for example, with Cornwall getting its own spaceport, and at all kinds of different scales and altitudes. And in fact, there's been a major shift in who is active in dominating those volumes over the past few years. So no longer is it about international space agencies with multinational agreements. It's about billionaires with money. We see that when we look up into the night sky now with Musk, who has put over 1,000 satellites into space for his Starlink project, and there will be 10,000 of those if he reaches his goal. Closer to Earth in the drone space, Bezos is dominating the debate over access to the airspace above our heads. And it feels really critical for us as scientists and users of this same space and the same technology to ensure that our democratic rights to access these volumes and to continue using them is not undermined by this corporate takeover. So I've also become aware that that space is very gendered as well. And so there's a few things that we've done to try to sort of actively engage in that debate and further it, and you can have a look at some of these examples if you like. One of the nice sort of accessible ones is the report that we wrote for the WWF, which is all about how we actually use drones to further conservation efforts in various parts of the world. So you can download that for free if you'd like. So conscious that I want to leave time for questions, I just want to finish up there and say thank you for coming, thank you for listening. And I want to also give a big shout out to all the people on this slide who have done most of the work that I've spoken about today, and who are responsible for the really great advancements that I've been able to share with you. So thank you.
Great, thank you, Karen. That was a wonderful talk, really enjoyable. I learnt loads, and it's great testament to the geographer and thinking about spatiality and spatial scale and how important it is. We've had a couple of questions in the chat already, so I don't know if Senthil, you want to put your camera on, ask your question yourself.
Thank you, Jane. Karen, it's fantastic talk. I learned a lot. You don't know, so I think 16 years of work in 1 hour is very difficult. I can understand that, but it's very eye-opening stuff for me, actually. So I have one question. So there are lots of polluted water ways throughout the world. And is that possible to take the images of those ones and then find out what type of pollutants are there, and then from the reflection of the light and other stuff? Is there anybody done this type of work before?
Yeah, so with optical data, so just red, green, blue data, you can certainly determine things like suspended sediment concentrations in water. If you want to look at kind of more biological activity in water, yes, you can also do that. It's a completely different beast to remote sensing of the land, because water is itself very dark and it absorbs a lot of incident light. So you have to have really good atmospheric correction procedures and things like that to be able to get a useful signal from water surfaces. But there are people here at Penryn who do work on exactly those things. So if you're interested, I can put you in touch with them.
Yeah, sure. I'll talk to you, through email.
Yeah.
Okay. Yeah. Thank you, Karen. Thank you. Thanks, Jane.
So you can look, Karen, afterwards at all the lovely comments that are flooding in here about what a fantastic talk that was and an amazing overview. But Gemma's got a question, so over to you, Gemma.
Hi, sorry. I just wanted to ask, you mentioned briefly about the new space in Cornwall. I was just wondering what it was and whether you could explain a bit more.
Yeah. I mean, I don't know a huge amount except for to say that it's going to be a place, because Newquay has one of the longest runways in the UK. It's a kind of candidate site for launching satellites into near Earth orbit, and I think Virgin are a part of that. The idea is to use kind of big 747s to get up to the kind of edge of space and launch CubeSats into space. So it's a relatively new thing, but it's quite a big international initiative that will be sort of launching from Cornwall in the coming months and years.
Anyone else got a burning question? Because there's 2 minutes left. I mean, it was very striking, your final slide with Jeff Bezos and Elon Musk up there, and the kind of new corporate frontier has become space, and I think that ties into the spaceport. Everybody's very excited about it, maybe partly because it's seen as the next industrial revolution, the kind of next big thing, even if people are not sure what's going to come of it. So your arguments about making sure the democracy is still there seem incredibly powerful and important. And G7 coming, these kinds of questions are going to be to the fore in the next couple of months. So it's really timely to raise them now.
I mean, I think space is transforming very quickly, and actually probably faster than legislation can keep up. And if we look at kind of recent satellite Earth observation missions really in space, there's a company called Planet, which is a private company. They've launched hundreds of CubeSats into space, and they were born out of a Silicon Valley startup. So it's very different from NASA and ESA, you know, who are using kind of multinational agreements and everything to get infrastructure into space. It's sort of separate from that, and it's a great opportunity, but I think it's also something that requires some careful kind of critical thought.
Yeah, definitely. Marcus has raised a point about Goonhilly Earth Station too. So again, that's another site in Cornwall that's all about space. And when you were talking, I was thinking that everybody hopes that the new farming regime is going to transform our region, and we're going to be farming for nature much more with the Elms farming system. So if we could find a way of using your new kind of user-friendly intersection with the Google Earth engine and map what's happening in our own region over time, I think that would be a really exciting project for the ESI, and something we should, obviously we're talking, but kind of promote over the long term to really track what's going on in our region. I see
absolutely.
Hand up. Let me quickly, whoever's got their hand up yet, shout out, please. Here he is. Hi. Oh, muted. We can't hear you. He's going to type his question. Can you read that, Karen?
Small vegetation, do you think? Yeah, so you showed an impressive 3D image of the volumetric vegetation for an area with sparse small vegetation. Yeah, good question. So do I think it would work over more dense vegetation? Well, that is a very astute observation. That is very tricky to do in coalesced canopies, and so that's why, for example, over the mixed woodland site in Cornwall, which I showed you, we were not able to do that for those tree species because the canopies were coalesced. With the photogrammetry, you need to be able to see the ground surface relatively close to the plant that you want to reconstruct if you want to produce nice point clouds of the structure of those plants. And so so it doesn't work very well in coalesced canopies, and that's where laser scanning really has the edge. But it does work very well in drylands, which is why we are using it in drylands, because there you have plants which are relatively sort of standalone and, you know, well distributed, and we can see the individual ground returns around each plant, which allows us to kind of reconstruct the shape and the volume of those plants really nicely in dryland systems. So yeah, you have to be careful about using those or assuming that they would work in denser canopies.
Yeah. Thanks, Karen, and thanks everybody who's come today. We're now out of time, I'm really sad to say, but I suspect that your inbox is now going to be full, Karen, with lots of people who've got lots of questions and lots of lovely comments too about what a brilliant talk it was, and very impressive to have that range of geographical locations and different kinds of applications. So really glad that you could do the talk today. A big thank you.
Thank you.
And hopefully we'll carry on having these conversations in the ESI as we go forward. So thanks everybody, and big thanks to Karen. We should give you a round of applause. Virtually, if not in reality, it's a great talk. Soon, hopefully in person, 3D.
Yeah.
Thank you.
Nice. Thank you to everybody for coming, and yeah, I'm happy to follow up with anybody afterwards. So
brilliant. Okay, thanks everybody. Bye.
Thank you. Bye.
Karen, you did a great job.